This is Hi everyone. Welcome to our Tuesday seminars on the cerebellum. So today we have Sam McDougle from Yale. Sam was a graduate student of Jordan Taylor at Princeton, and then did his postdoc with Ann Collins at UC Berkeley, and a couple of years ago set up his lab at Yale. I'm very proud to tell you that he is related to me through the academic world because he's my great grandson.
Yeah, that's great.
Sam, thank you so much for being here.
Yeah, thank you, great grandfather, for having me here. It's my pleasure. I want to say off the bat, I'm really excited to be invited to this, and I hope you all won't be disappointed by hearing from a psychologist in this amazing, mainly brilliant systems neuroscience seminar. So hopefully I'll either be confirmation bias if you don't like psychologists, or maybe I'll change your mind. No, just kidding. But yeah, it's great to be here. I want to present a series of studies done in individuals with cerebellar degeneration over the past few years that I conducted. Actually, I started this project when I was in grad school with Jordan Taylor. And then when I began my postdoc at Berkeley, doing more work on computational work and reinforcement learning and things like that, the project kind of was in hibernation mode. And we had some exciting findings from two experiments, but then we were in hibernation mode. And then JT Say, who is a graduate student right now in Richard Ivory's lab at Berkeley, revived the project beautifully, I think. And we realized that we thought we had a really interesting story that fit with some intuitions we had going in. And so this is, today I'll talk about that paper, which is just coming out in a couple of weeks, actually. And we'd really love feedback on future directions and things like that. Okay, let's get started. So just a quick roadmap of what I want to go over in the next 35 minutes or so as I present this project. The first thing I want to do is lay out some assumptions, 2 or 3 assumptions that I want to work from when we think about the cerebellum's role, potential specific role in cognition. These are assumptions, and so I want people to feel totally free to interrupt me and challenge them and critique. But I think maybe starting with these assumptions will help make sense of some of the more kind of abstract intuitions that we brought to this project, things that might seem a little bit speculative, and I want to kind of upfront sort of lay the foundation for those speculations. And mainly what that's going to lead to is me talking about something that cognitive scientists like myself are really interested in, which is covert actions of the mind. Okay, so things you do in your mind covertly that we can call transformations or manipulations. Those things are similar, that are done on, let's say, thoughts or mental images. And drawing the connection between these mental manipulations and manipulations we actually do in the real world with our body, which are things I know everyone here is interested in. Trying to bridge those things will hopefully be seen as like the kind of fundamental goal here. And then I'll present 2 studies. The first study is looking at the cerebellum's potential role in mental rotation, and I'll explain what that is in a moment. And then a slightly more controversial or speculative kind of pivot to another type of mental task called mental arithmetic. And then finally, I'll try to summarize and give some limitations and critiques of some of these concepts and thoughts about moving forward on understanding cerebellar cognition, as it were. I found this comic online actually recently. I'm surprised I hadn't seen it before, that I thought was cute. And I just put it here just to kind of make the point that all of us here are in agreement, I assume, that the cerebellum very clearly has a role in non-motor behavior. I'll be general like that. And that role is pretty clear at this point. But I think we also all can acknowledge that what that role is somewhat vague and understudied, and really is something that people are really just starting to sink their teeth into, I would say, over the last 10 or 20 years. So I'm going to lay that out as an assumption that we all follow, that the cerebellum contributes significantly to cognitive behaviors, and there's lots of evidence for this from a lot of different avenues. So one avenue is an anatomical avenue. I'm highlighting the work of Peter Strick here. There's other work that has shown the same sort of results, which is that you have these massive actual bidirectional connections between the cerebellum and areas of the frontal cortex and associative cortex that are, a cognitive neuroscientist would tell you, are sort of key areas of many cognitive behaviors and behaviors that don't have any obvious connection to motor control or motor learning. There's also correlational evidence from a bunch of different sources. The sources most close to what I do in my lab, being a human neuroscientist and psychologist, come from things like resting state connectivity, so work from Andy Buckner et al., showing that if you just look at baseline correlations between bold activity and a person laying down in the scanner, hopefully not sleeping too much, you'll see that these networks sort of emerge that connect multiple areas of the cerebellum, and actually importantly not constrained by its lobule boundaries, and areas all over the neocortex, specifically, again, including areas of the PFC and association cortex that we attribute to a lot of high-level cognition. So that's a really nice paper. And I would say this work's really been taken really far in what I consider a kind of landmark recent paper from Maeve King working with Richard Ivory and Jorn Diedrichsen, where they had human subjects perform a marathon in the scanner of a bunch of different cognitive tasks with different types of cognitive demands, and showed a couple of interesting things. One thing they showed is that this functional map in the cerebellum did not seem to follow the lobule rules, if you want to put it that way. So it seems like there's this functional map that abides by its own kind of structure. But the kind of big thing I like about these findings is really just showing how the diverse set of cognitive tasks that are heavily implicated in cerebellar activation as measured by bold signals in fMRI. And finally, most relevant to the thing I'm going to talk about today is that there's a lot of causal evidence in humans that the cerebellum plays a role in cognition. And Jeremy Shadmehr has kind of been the main person to really publicize a lot of these rather consistent cognitive and affective presentations that you see in individuals with cerebellar degeneration or damage from stroke, things like that. And so putting this all together, there's a pretty wide story about the cerebellar's role in cognition, and other labs are now kind of picking this up and looking at the role of the cerebellum in development as well. So I'm highlighting a paper from Alexandra Badura while she was still in Sam Wang's lab that I think is also a really kind of landmark paper showing these rather important role for the cerebellum in normal cognitive and social development. Okay, so that's assumption one. I imagine we're all kind of on board for this. Assumption two is probably the more tricky one. And assumption two here is that the cerebellum is a module, that is, it is functionally a kind of suborgan of the brain. That's a controversial idea, I know, so I'm happy to defend it a little bit. But also the maybe more tricky part is that we can maybe make a guess that it performs a specific computation that is translated across task domains. This has been called, again, also by Shadmehr, this universal cerebellar transform is the phrase. I think it's a nice descriptive phrase. I'll note that Jorn Diedrichsen actually has a review that came out around the same time as that paper from Maeve King that I think makes a good point of the alternative hypothesis here. But I'm just going to go with it for now as an assumption. And this assumption is built off of just the general stereotypy you see across microcomplexes in the cerebellum, which has led some physiologists to kind of assume that the general computation that the module of the cerebellum performs is probably performed by these sort of repeated circuits. That's, again, I note that this assumption is, I'm calling it an assumption because that's really, I still think what it is theoretically. I don't think it's a axiom or anything. Okay, so what form might, if that computation that we think the cerebellum performs across task domains is real, what form might it take? How can we start to make sense of computations that the cerebellum performs for sensory motor control, for example, and kind of graft them onto cognitive tasks? And I think this is a big question. And what I want to make clear is that I think the studies we have here are one very specific attempt at this. It's not an attempt to generalize the cerebellum's role in cognition. It's not an attempt to have an overarching theory. It's an attempt to just sort of start to kind of peel back from this assumption and see what's underneath when you try to take computations that make sense in sensory motor control and translate them to cognitive tasks. And we were totally inspired by previous authors. We pulled none of these ideas out of our head. So for example, in a kind of classic paper by Leiner et al. In 1986, there's this nice quote. I'm just going to read a couple quotes here. It's going to be a little bit like an English class for a moment, but bear with me. Leiner and I'll say that signals from the older part of the dentate nucleus certainly help the frontal motor cortex to affect the skilled manipulation of muscles, and signals from the newest part of the dentate nucleus may help the frontal association cortex to affect the skilled manipulation of information or ideas. So the emphasis is mine there. Shadmehr has a phrase he's used before called the dysmetry of thought. This is a hypothesis that in the same way as the cerebellum regulates the rate, force, rhythm, and accuracy of movements, so may it regulate the speed, capacity, consistency, and appropriateness of mental or cognitive processes. And my favorite quote here is from Ito in a paper in 1993, where he states that in thought, ideas and concepts are manipulated just as limbs are in movement. There would be no distinction between movement and thought once encoded in the neuronal circuitry of the brain. Therefore, both movement and thought can be controlled with the same neural mechanisms. An obvious question that follows is, what is the dynamics or inverse dynamics model of an idea or a concept? To answer this question, it's necessary to know their representation in the brain, which is as yet unclear. So I think Ito's really laying it down really clearly here that what we want to look at is mental computations that are analogous to motor computation. And he uses these concepts, well-known concepts of forward and inverse models that he, of course, is famous for helping connect to cerebellar processing, and arguing that maybe we can start to replace some of the variables in here with non-motor variables if we understand the cognitive domain we're interested in looking at. And so our wager is kind of inspired by those sort of ideas, is that if we can come up with some good psychological constructs, ones that are already out there off the shelf, of cognitive representations that might require the sort of internal mental manipulations or internal models, to use Ito's verb there, that are used in sensory motor control, that could help us start to maybe operationalize some of these intuitions, which is really hard to do. These are very abstract intuitions. Okay, that's a really long intro. So what do we want to, how do we want to do this? As a cognitive psychologist, there are certain papers I read in undergraduate or early in graduate school that had just stuck in my head. And I'll talk about one in a moment, but I consider it both a strength and a flaw when papers get stuck in your head. It's a strength because then you can remember it and highlight it. It's a flaw because maybe all of your thinking is now magnetized to those papers. But I'll talk about one right now that really stuck in my head and kind of framed this project. But the basic assumption now, assumption 3, if you're keeping track, is that I think there's pretty good evidence in cognitive psychology that truly analog or continuous transformations can be performed on mental representations. And I'll tell you what that means now with an example. Okay, so the classic example to me, and this is the paper I was just mentioning, is the example of mental rotation. I'll note that the results of this classic paper might seem rather obvious, but in 1971, they were really an important sort of counter to the behaviorist thinking that had really dominated the first half of the 20th century. And these kind of papers ended up being really influential in the cognitive revolution. So I'll just throw that out there. So what do I mean mental rotation? Well, it's rather simple. I'm going to give you an example now. If people you can unmute if you want, or just stay silent, but I want you to tell me, I'm going to show you 2 shapes. And I want you to tell me if these 2 shapes are the same or different, okay? Any answers? I don't know how many people know this paper on this. Yeah, what about these 2?
Different.
Does anyone want to report what they did to answer this question? Or you don't have to if you're bashful. Might have, yeah, right. You rotated it in your mind. Okay, well, mental rotation's on the slide, so I primed you. So the key result of this paper from Roger Shepard and Jackie Metzler, and this has been replicated countless times since then, is that the task I asked you to do, which is to make a same different judgment, was irrelevant. Actually, what really mattered is how long it took you to do it. That's really what is measured in this task. And the very provocative result that Roger Shepard and Jackie Metzler found is that the time it took people to do this task was linearly related to the rotation they would have to do had they been holding the objects. In other words, the difference between the objects in three-dimensional space, the degree of difference, almost perfectly predicted the reaction time of the subject. And this is a really kind of nice quantitative demonstration of the qualitative report of having rotated these objects in your mind, right? Well, if you do rotate them in your mind, they should follow the laws of physics somewhat of the real world, such that you should get this continuous reaction time effect. Turns out you can actually have people also rotate the objects. So this is a study done in kind of a very precursor VR kind of study where people both did the mental rotation task I just told you, where they just do it in their mind, and then they also do it on a knob. And what these authors found, if you look at the difference between the zero conditions, is the reaction time functions. They were linear again. Here I'm folding them across angles. And they're also equivalent for mentally rotating the object and physically rotating it, which is a rather strong demonstration of, I think, the interpretation of this effect. Okay. Why do we want to do this task? Well, the reason I really like this task, aside from just having that paper stuck in my head forever, is that this task gives us a metric of behavior, a non-motor behavior, that goes beyond accuracy. You know, I don't want to be too critical, but I do think accuracy metrics are problematic for the kind of obvious reason that a lot of different factors can shape an accuracy metric. Things like fatigue, things like control of your eyes, things like motor demands, things like prescription drugs, right? And so I think a lot of the findings in individuals with cerebellar degeneration have been really useful in sort of framing this range of cognitive problems. But I also think that we should start to try to maybe go beyond accuracy for all the reasons I just mentioned. And so I think this slope metric tells us something about like a mental kinematic process that is that can be sort of abstracted away from all the confounds in an accuracy metric, I hope. Any questions so far? I'm kind of, okay. So just to kind of put a fine point on it, the argument here is that certain types of cognitive computations or transformations like mental rotation would sit on what Jeff Miller called this sort of spectrum between continuous and discrete mental computations. And his example of a continuous computation is itself actually mental rotation. And his example of a more discrete thing is something like mental comparison. So maybe between these two red images. And he makes a really strong point here. This is a spectrum. I'm not making an argument that there's some binarization that a psychologist can do between a continuous and discrete mental computation. That's clearly too simple. It's all complicated, but at least at the high computational level, you can at least draw a line like a spectrum and put a task presumably somewhere along that spectrum. Okay, so let's go to the data. This is the paper that's coming out in a couple of weeks, and I'll show you the 4 experiments from that paper. And I want to mention that JT Say, who I already mentioned, has really been a great contributor to this and is a co-first author on this whole project. So mental rotation in patients with cerebellar degeneration. Across the studies I'm going to show you, we had 48 patients. We had a bit of a range of diagnoses, and I'll get into that a little more if people want me to. You know, optimally, we would have had 48 individuals with SCA6, but we didn't have that for this particular project. But I'll note that a lot of the analyses I show you we replicated them all with certain exclusions or within group comparisons to really make sure that our effects weren't driven by one particular diagnosis or by maybe diagnoses that have been heavily associated with extracerebellar effects like SCA3 being the strongest one. So I want to just flag that here, but I'm happy to talk more about it. And then we have control subjects who are matched in age, handedness, sex, Montreal cognitive assessment, which is just sort of a baseline, are you with it sort of cognitive assessment, and then years of education for 3 of the 4 experiments. We did not do that in the first experiment. Okay, so experiment 1 is a mental rotation task, a classic off-the-shelf mental rotation task The difference from the one I showed you only being that it's in 2 dimensions and doesn't involve novel shapes. We wanted to remove the effect of those novel Tetris shapes that require kind of eye movements. We didn't want eye movements. So we have nice big white letters in the middle of the screen, and their task is not to say whether something's the same or not. There's no comparison task now. It's just whether the letter is normal or mirrored. And so oftentimes to do that, answer that question, you have to mentally rotate the letter upright and then make the judgment. This is actually a task Roger Shepard himself came up with as a sort of simpler, less baggagey version of the Tetris task. And what we're going to ask is, does the amount of rotation that a subject has to do linearly predict the reaction time? But more importantly, what's the pace of that mental rotation process? Do we see essentially mental dysmetria in the mental rotation process? And sure enough, that is what we see. So individuals in the cerebellar group showed a higher intercept, kind of classic finding, and I'll talk about whether that's problematic or not. So much slower reaction times on the whole, but also a disrupted mental rotation pace. Okay, and by the effect size was rather large. I'll note it's a small sample with SEA patients, so the effect size should not be overly interpreted, but we did get a rather surprising effect where individuals with cerebellar degeneration had a notably disrupted mental rotation process. Now, you might be wondering, there's probably a lot of thoughts you're having about some controls, and hopefully we'll hit most of those now. So, yeah.
Just to be clear on the results that you showed in the previous slide.
Yeah.
Yeah, so that's the slope on the right side, is that right? The slope.
Yeah, we did it in units of pace because that's the more standard way we've seen it in other papers. Yeah, they put time over the degrees rather than the opposite. Yeah.
Thank you.
So it's a speed, it's a pace, not a speed. Yep.
May I ask a quick question?
Please.
So where do we know that the difference in reaction time is only associated with the cognitive part of the task?
Yeah, I'm going to try to get at that in a moment. If you can bear with me, hopefully I'll answer that, but then I'll return and ask you again if I did. Does that sound good? Okay.
Sure. Thank you.
Yeah. I think that actually your question there's multiple versions of that problem here. So hopefully I can try to get at that. So one question first, if we want to get at whether this is measuring the cognitive construct that we think it is, one question is to ask, is it really just specific to mental rotation, or is it just that we're seeing a deficit in processing speed that carries over into this mental rotation slope? And so to us, the most kind of convincing way to answer this, aside from saying, well, there's decades of mental rotation papers and the slope is really about mental rotation, and there's some evidence that if you stop someone in the middle of it, they're halfway rotated, which is kind of what you'd expect, et cetera, et cetera. But really what we thought we needed, and I can say Rich was instrumental in making this happen, was to have control tasks. So essentially have tasks where we see a reaction time slope that's linear because of some kind of cognitive process, but one that doesn't have this flavor of a continuous dynamic mental transformation. It took us a while to kind of put our heads around what kind of tasks look like that, but then we returned to the cognitive psychology literature, and the task that made the most sense to us was what's called the Sternberg task. This is another sort of simple task, also was kind of a nice discovery in the middle of the century. And how the task works is people are shown either one by one or as a group, it doesn't really matter, a set of stimuli that they have to remember, called those the memoranda. And then after some delay, they're shown a stimulus and they have to judge whether that stimulus had been in the original sequence or not. And you get a nice reaction time, linear reaction time effect, just like we wanted, but one that doesn't have the flavor of this dynamic mental kind of kinematic transformation, but has more of the flavor of memory retrieval and then maybe discrete comparison between retrieved memories, which we didn't feel as cerebellar to us for the vague reasons I told you. Okay, so we did, again, we wanted to do a version of this task with really big stimuli, big color differentiations, avoid any eye movement problems or sensory processing. And so people saw these large textures, sort of fractally textures, either a sequence of 1 to 5 items, and then we're given a probe and had to make a same different judgment, or old new judgment, excuse me. And here we got the linear effects in both controls and cerebellars, but the critical result here is that we did not see an effect of cerebellar insult here on the mental retrieval or mental scanning pace. I guess retrieval is better. So, or search, I guess is the word we came up with. So the idea here is that we thought this was a nice control because there is still this linear cognitive process that takes time. The assumption, according to Sternberg, is that essentially you're either retrieving multiple items in parallel or maybe even retrieving them in a sequence. There's a debate about that, but either way, you're retrieving things and comparing things. You're not transforming things in a way that would require a sort of predictive internal model to do so. Okay, but there's another complaint maybe you're having in your head, which is that, if we think these two studies are measuring different these two tasks are measuring different cognitive processes, we should be able to kind of analyze that because all the same subjects did both tasks. And so we did find that the baseline reaction times, so the intercepts of those functions, was correlated across this memory search task and the mental rotation task. And I've just, for visual here, I've just mean centered each group just so we can put them all together. We found this individually in each group. This is a low end correlation, by the way, so grain of salt. But what we also found, which is what we expected, is that we did not see a relationship between the paces or the slopes of the two tasks. And so the assumption there was that, sure, it takes patients longer to respond in whatever task you give them. So their baseline reaction times should be correlated between these two tasks, or really any tasks we give them, because the baseline RT doesn't measure that cognitive process. The baseline RT measures more sensory motor, basic kind of processes. But then these slopes, which actually tell us something about the mental computation, presumably, those should not be related. So that's what we found. We found that across experiments. I'm just showing you here. Finally, you might be wondering, is this just like maybe this is about spatial cognition? Not that that's like a problem necessarily. That would be an interesting discovery if that's really what we found. But we did want to kind of rule out that this is just one task is sort of spatial. Mental rotation has a spatial flavor to it, and the Sternberg test doesn't. It's purely visual matching. And so first we wanted to replicate the mental rotation result. That's important in these small samples. So we ran another sample of different subjects on the exact same mental rotation task and replicated the main result, which was this difference in slope between the controls and the patient. So that was nice. But then we ran a version of the Sternberg test. We sort of invented a version that was, instead of being abstract visual textures, it was locations on a circle of discrete memoranda. So you're discretely remembering where these dots are, and then you're retrieving that memory to make the old new judgment. And in this case, now people's response is 1 of 5, which is the order in which where in the sequence of dots they saw the probe fell. That's right. And again, we got this linear reaction time slope, which was nice because this was this novel task we came up with. So that was a good sanity check. But again, we did not see this dissociation between the groups. So that sort of fit that maybe this is not just a general spatial cognition thing. We also wonder, are these effects driven by maybe differences in a speed accuracy trade-off? So if you imagine the patients at bigger rotations, they might sacrifice time, so spend more time to make up for some kind of issue in accuracy, right? And so what we could see could actually be confounded with some sort of modulation in the speed accuracy trade-off that we see in the patients, but not in the controls, which would certainly be a confound in our interpretation. But luckily for us, the speed accuracy trade-off was equivalent essentially across groups. I'll actually note accuracy differences. We saw them both in mental rotation and memory search. They were actually bigger in the memory search task. And I can't tell you why the accuracy differences happened. And I think they're interesting and important and maybe even a little problematic for our interpretation. That said, all the interesting stuff we've seen and replicated with the slopes told us that, again, maybe the accuracy metric is not, it's harder to say what's going on with an accuracy metric than with a slope one. And we saw similar accuracy results in both studies. And we also, you'll note there's some people who were really bad at the mental memory search task. We made sure to analyze people who were good at it, as well as like a additional analysis to make sure that our effects weren't driven by those folks. Okay. So, you know, the high level interpretation, speculative interpretation here, very speculative, is that what's going on in dysmetria, we know with cerebellar patients, there's an analogy here that we can grab onto between kind of dysmetria of movement and dysmetria of mental movement, as it were. Yeah, so now I'm gonna kind of pivot into the little bit more kind of maybe controversial or speculative aspect of the study, but one that we were still excited about, which was, can we kind of think of another set of tasks way different than this one? So not just replicate, we already replicated the mental rotation one, but can we think of another kind of domain that has this flavor of sort of mentally moving along some sort of representation? And so I'm going to talk about the mental number line, which is a kind of fun concept in cognitive psychology that I imagine some of you might not know about, and how the results we got there in the patients. So there's pretty good evidence, I would argue, that people, and actually even maybe like baby chicks and actually now insects, there's a PNAS paper a couple of weeks ago that insects might have, like bees might have a mental number line. But what do I mean by mental number line? Well, the concept is that there's some sort of orderly analog representation in your head about number, and that actually when you do certain types of manipulations of number, you actually move some sort of internal attentional spotlight, if you will, maybe. You move it along this continuous mental representation. It's discretized by Arabic numerals, but studies have shown that, you know, that's just a function of language, but actually it might be this kind of continuous attentional vector. And so the original study that started to get at this was done by Stan DeHaan in the 90s, and it's been really built upon a lot since then, but I tell you the original study because I think it's great. So in this study, people made really simple greater or less than judgments. They saw the number 5, and all they had to do was say whether a number that they saw was greater or less than 5, right? Seems like the least interesting task you could have. But the key manipulation here was that there was a compatibility, a handedness compatibility manipulation underneath this relatively simple task, which people were all performing at 100%, which is that trials could be congruent spatially such that the probe was higher than 5 and the answer involved your right hand, or trials could be incongruent such that, let's say, the probe was higher than 5, but the correct answer was with your left hand. So they could change the mapping between hands and answer less than and greater than. And by changing that mapping, they can set up this situation where if you're attending to the right side of your mental number line, that would bias you towards your right hand. And if you're attending to the left side of the mental number line, that would bias you to your left hand. And what you'd expect, which is what they saw, was this kind of crisscross effect, which is, I think, a really beautiful result, which is that you're essentially primed to make responses with your right hand. Essentially, you're primed for your right effector when you're in the right part of your mental number line, and vice versa. Now, I imagine right now you're skeptical of this interpretation, and hopefully the next result, which I think is really cool, makes you somewhat less skeptical, which is this paper by Zorzi et al. In Nature. I recommend reading it if you haven't. It's about, like, I don't know, a couple hundred words long, I think. So they took this idea into neuropsychology, into a patient group, and asked them very simple, even simpler tasks, arguably, maybe not, which is they give them an interval between two numbers, and they just ask the patients, what is the midpoint of this interval? Okay, symbolically. So just give me a number that's the midpoint of this interval. Obviously, the answer to this question here is 13, right? But critically, these were patients with hemispatial neglect, okay? And specifically, it was 4 individuals who had neglect of the left side of their visual field and thus were biased to the right side in terms of their attentional acuity. And what they found was that it's really a wild result, which is that patients with this specific right hemisphere lesion, so left hemifield neglect, showed this bias in answering these interval questions towards the right side of their putative mental number line. In other words, they were more likely to say that the interval of this example problem is 14 than they were to say that it was 12. Okay, so they were deviated based on their neglect in their mental number line. That's the interpretation that the authors have in this paper. You can see control subject didn't have this bias. And then they had another patient group who had other types of cortical damage that was not neglect. And they also didn't show this bias. People showed variance, so they might make mistakes in this problem, even though it's a simple problem, but that variance wasn't skewed in any direction. It's interesting because this really matches results seen in the physical line bisection, right? So when you actually ask these same neglect patients to bisect a physical line, you show them a line and you say, draw a line down the middle, you see this exact sort of kind of bias towards the area of their visual field that's not neglected. So I don't know, I think this is a pretty cool idea. I'll keep going through some more because the mental number line I know is more novel than mental rotation. There's another set of findings that's really cool that you can actually train a machine learning classifier on fMRI data to decode whether someone is saccading to the left or the right. This is in the posterior superior parietal lobule specifically. So you can train that decoder to do that and then test it on a task where the eyes are held fixated, but people do addition or subtraction. And addition is supposed to involve moving to the right of your number line as you iterate on an operand. And subtraction is supposed to involve moving to the left of your number line as you iterate down off of an operand. And they found that they could actually classify addition and subtraction pretty well using a classifier trained on saccades. So again, the argument here is that you're sort of continuously moving your attention along your mental number line. Just like mental rotation, it's this continuous movement done in covert mental space, not in overt eye movements. Oh, sorry, one more just because I like these. There's another cool study showing when people, you do simple addition problems and you give them a set of answers, all of which are wrong. And you again ask, are they biased in a particular direction in their answers? And the answer is that for addition problems, people tend to be biased towards solutions that are higher than the answer. And for subtraction problems, people tend to be biased towards solutions that are lower than the answer. And the assumption here is there's some sort of operational momentum on your mental number line where you're, as you're kind of attending to one particular direction, you're more likely to sample an answer that is higher than the truth than lower. Okay. Oh God, I have so many of these. Oh yeah, right. So this one is a basic one for us. This is just showing that you see these linear reaction time effects. As you'd expect, if you're moving along your mental number line, it should take you more time to go more distance. And so what's been found is regardless of whether people seem to be operating off the minimum or the maximum operand in a simple addition problem in this case, which is what we're going to use as our test bed, you get this linear reaction time effect. You get this increase in reaction time based on the magnitude of the operand. It turns out the maximum operand is a better predictor of reaction time, but that's kind of irrelevant. So that's called the problem size effect and was discovered and connected to all this mental number line stuff and inspired us to try this in patients. And so what we're going to do is have people do these simple true-false judgments on addition problems, really easy task. The key point we're going to ask is, does the size of the maximum or minimum operand, we're going to focus on maximum again because that explains the data the best. Does the size of that operand, in other words, does the amount of movement you have to do from whatever your starting point is on your mental number line, does the amount of general movement you have to do along it, in this case, in the positive direction, increase your reaction time linearly, and more importantly, does that increase, does that process of moving along your mental number line while you solve these tasks, is that disrupted in cerebellar degeneration? And long story short, we found that it was. So I'll note here that both of these slopes are significantly, or paces are significantly positive. It looks a little subtle for the controls, obviously, but we found a rather large effect size where cerebellar patients seem to have a disrupted mental number line scanning process, to put it in a jargony way. And so we thought that was cool. Now, definitely need some controls here too, right? There's a lot of alternatives. One is, well, is it just about, maybe just number processing is harder for them. Certainly here, like eye movements, we're still doing really big numbers and trying to avoid any kind of obvious saccade requirements, but these are more complicated symbols than like a bright red fractal or something. So this is something that you might actually have to scan. So anyway, we wanted to see if like just processing numbers was a problem. And so we did what are called these tie problems, which some old school psychologists found do not have the problem size effect. So 6 plus 6 takes you as long as 2 plus 2, even though for 6, you might have to move further up your mental number line to do those problems. But something about ties, it seems like you just retrieve them from memory. These are things you learned as a child that you just immediately retrieve from memory. And sure enough, we saw no significant slopes here, and also the slopes were not significant. The slopes we did find were not significantly different. It's kind of irrelevant because we didn't find a significant slope anyway. Now you might also wonder, is the problem size effect, is there another problem size effect we can use so we actually get a slope, but one that's not thought to require number line scrolling or this mental continuous movement of attention through your number line? And the answer is multiplication. So multiplication does have this, if you compare small multiplication with small or large operands, larger, it takes longer, and actually activates a different brain network, which I think is really fascinating. I'm going a little fast here because I realize I'm too slow. Anyway, we replicated the addition result first, so that felt nice. And then we tried this multiplication test, which people have shown through a lot of different means in cognitive psychology have shown that seems to require just retrieving from like a multiplication table if it's a small enough problem, one that you learned in grade school, for example. And here we saw the significant slopes. The argument for those is that multiplication problems with smaller numbers are actually stronger in your memory because you learn those first and you have more repetition with those. And so that's the argument for these multiplication slopes. And there, again, we saw no difference between the groups. So we thought that was a nice internal control. And the speed accuracy trade-off, again, did not seem to predict the results. Right. So let me try to just speed through my ending points here. So first, to summarize, the concept we wanted to bring to this study was that ideas about coordinating continuous sensory motor transformations that the cerebellum helps with, can we analogize that to something in the cognitive domain? Mental rotation being to us sort of the kind of prime example, though we think movement along the mental number line is an intriguing secondary example. And we found in both sets of those types of tasks, this deficit in the mental computations, but not in tasks that we consider to be somewhat reasonable controls. And I just want to give one little aside here that there's actually a fun, interesting set of questions out there about a really interesting observation in cerebellar patients during visual motor adaptation tasks. Now, we all know when you do these visual motor adaptation tasks, let's say learning to counteract a 45-degree visual motor perturbation, it's been well replicated that cerebellar patients struggle with these tasks. And if you isolate the part of their adaptation curve that seems to really reflect like implicit sensory motor recalibration, you find that they're certainly impaired at that part. That's been well replicated. But also it seems to be the case that they're also impaired at kind of explicitly figuring out how to replan their movements or re-aim their movements. And I think that's been an interesting sort of open question is why would a cerebellar patient have trouble re-aiming a movement? What's cerebellar about that? Well, I have some data that was inspired by older papers from Georgopoulos actually, that when people do re-aim their movements in continuous space, they seem to do so in a way that's analogous to mental rotation. And so you can test this actually pretty easily, just give people a bunch of different rotations that they have one trial to counteract and take a big average. So people see some rotation, then they have to counteract it with a movement. We can measure the reaction time. And there's this linear relationship, just like mental rotation. So maybe re-aiming your movement is kind of like mental rotation. So maybe the reason cerebellar patients are bad at re-aiming their movements is because it requires this continuous mental transformation, presumably. And actually, JT has a paper I wanted to highlight that just got put on bioRxiv, where he shows that cerebellar degeneration impairs the discovery of these strategies, these mental rotation, presumably re-aiming strategies, so replicating the Butcher paper. But then when they need to recall them, they're fine. And so the argument here could be you're doing mental rotation here, and you're doing memory retrieval, like the Sternberg task over here. And that's why patients have this deficit, specific pattern of deficits. Okay, so I'll just end on some open questions and caveats and problems. One problem is that I think there's a decent argument that this universal cerebellar computation concept may just actually be misguided, that maybe we shouldn't worship at the altar of the microcomplex and assume that that means there's a universal computation that the cerebellum performs as a module, but that actually it could be a uniform circuit that still has multiple functions at the algorithmic level, and that produces the variance we see. So I think that's an important thing. And I guess I want to believe in the universal cerebellar computation idea, but I'm certainly not a partisan. Even if we do take the universal cerebellar computation idea seriously, which I think is worth it, there's still a lot of different effects that we need to synthesize. So like Rich Ivory himself has found a lot of different cerebellar patient deficits that aren't specifically related to obvious, motor kind of things. Things like interval timing, some tasks involving predictions, things like that. And so there's actually different ways to account for what this transform might be, even at different sort of levels of analysis. And I think synthesizing all these things is important. My personal belief is that maybe our way to make sense of the cerebellar's role in all these tasks, assuming it has a causal role in all these tasks, first of all, we shouldn't assume causal role. That's item number one. And item number two is maybe we need to kind of think bigger about how to relate, in my opinion, timing and prediction as being a way to come up with a more abstract computational description. And I just want to say that you might think that this work, and I agree with you if you do think this is kind of top down and a little bit psychologizing cerebellar cognition, coming at it from a kind of as top down as a place you can, and inevitably that's going to be a speculative exercise. And maybe it's pitched at the wrong level, like maybe thinking about task, mental computations and mental rotation, like maybe that's not actually the right level we should be at to understand the cerebellum's role in cognition. And to that, I think that's a good argument, and it could be true. But I want to just leave you with this kind of fun quote, and I mean this in a totally tongue-in-cheek way, but I want to, this is a Dan Dennett quote from 2006. He says, if you want to know what a chess-playing computer does, forget about trying to understand it from the bottom up. If you don't understand the conceptual domain in which the topic is chess, moves, and strategy, you'll never make sense of what happens. If we're going to use this top-down approach, we're going to have to be speculative. The dangers of this top-down approach, of course, are many. Speculation is guided largely by plausibility. Plausibility is a function of our knowledge, bad habits, misconceptions, and bits of ignorance. So those who have no taste for this sort of speculative exercise, which is fine, will just have to stay in the trenches and do without it. And the rest of us can risk embarrassing mistakes and have a lot of fun. Okay, that's just a fun Dan Dennett quote. And with that, I'll say thank you to the collaborators on this project and take some questions if you have.
Well, Sam, that was just fantastic. I absolutely loved it. Thank you so much.
My pleasure. It's fun to give it. I hope it was thought-provoking at the very least.
Let's pause and let's see. Let's pick some questions.
Hi.
Hey, Shaza.
Hi, Sam. Thank you very much for your wonderful talk. I have a question for the site or the responsible site for the mental rotation. Where in the cerebellum is responsible for the mental rotation?
Yeah, that's a great question. I know I have a slide somewhere. Just give me a moment. It's not in this talk. Sorry, I have to search my Keynote folder here. I know that it's been found, the cerebellum is highly active during mental rotation.
I see.
And I believe it's cruise 2, but I think I could be misremembering. But there is an answer to your question, and I have it in another slide, I think, but it might be on the internet right now.
So if I remember correctly, for cruise 2, the right side of the cruise 2 is responsible for the language processing, and probably left side of the cruise 2 is spatial processing. Then the left side, the is left side cruise 2 is more for your mental rotation, right?
I don't know. I don't know. Let me
Okay,
find out.
okay, that's good.
I can tell you that I can say that it's messy. Oh, here we go. That's what I'm looking for. I was
Okay.
just Googling Catherine Studley. That was what I was Googling for. Yeah. So I was right about cruise 2, but it also looks like cruise 1 and lobule 7B.
I see.
And even
I
into
see.
lobule 6, if you look at this panel. So this is the paper I was Googling for. Let me see if I can.
And probably left biased, right?
Is that figure enough for you, or should I Google for this stupid paper? I can find the whole thing.
Yeah, I think that this is enough. This is perfect. Yeah.
Okay.
So another question is, I think for mental rotation, the cooperation with the cerebral neocortex should be important. I think the cooperation with between the cerebellum and the neocortex should be important. So then do you have any idea for the cooperation with the neocortex?
For mental rotation and cerebellum?
Yeah, for mental rotation. Yeah.
Yeah.
Or
I don't know if someone's done like the connectivity analysis. I guess Maeve in her paper, I know they did mental rotation. So she, I guess, has the data where she can look at functional connectivity between cortical correlates of mental rotation and cerebellar. But as far as I know, I don't know if people have done the connectivity analysis, but mental rotation does activate parietal cortex and premotor cortex. And so there's actually an argument that mental rotation is actually like mental simulated movement of the hand. But I think that evidence is sort of mixed. But there's some people who would argue that actually when you're doing mental rotation, you're like covertly, without actually executing movements, you're sort of covertly activating like hand area because you're thinking about moving the object with your hand. But I think that works a little bit. I think there's like a mixed opinions about that in the field. So I'm kind of agnostic on that. But yeah, you definitely parietal. Yeah. It's considered like a sort of working memory manipulation. So it's like a classic spatial working memory frontoparietal network.
I see. That makes sense. Thank you so much.
Can you see the figure now from Catherine Studley? I was trying to Google it. Okay.
Well, I might have a question, Sam. Thanks for the very nice talk. So you seem to relate this mental rotation ID and the line number to more the explicit component of motor adaptation. That's both are kind of mental rotation or moving along sometime or some kind of representation. But how do you relate that to the implicit component of adaptation, which is kind of different in my opinion? Any thoughts on that?
I think that's a great question. I actually think that question gets at the core question I have about all of this, which is how could I even relate mental rotation to like Iblin conditioning, right? Or to any sort of, I guess, to like any sort of cerebellar sensory motor learning. I'm tempted to just throw the question back at you and see what you think. Because the answer might be it's a doomed endeavor. I don't know. I think maybe there's something there. I mean, Rich, certainly, if you ask Rich, I think he would say that predictive processing that requires a short temporal scale is one place to start funneling things down. And so if you think about mental rotation and you tried to like write down what you're doing mathematically, it would have a high granularity, like the time intervals are really small. And actually that's what this psychologist kind of argued is what makes something a continuous mental transformation, is that it has high granularity of time, of points in time. And so I think maybe there you could start to say, well, implicit we know has that too, right? Like you need to have a relationship between planning and feedback, or action and feedback that's like really tight, because you're building a model that continuously predicts those things in real time, predicts that relationship in real time. And so you could consider moving a Tetris piece in your head as sort of continuously predicting that next step in the forward model. That, I'm totally hand waving, right? I don't know. I totally don't know. I think maybe, again, if this is pitched at the wrong level, the answer won't be something I can explain. It would be like, oh, it's all about just like high dimensional cortical cerebellar dynamics, or low dimensional maybe cortical cerebellar dynamics. And I've just chosen a set of tasks that happens to sort of mess with those dynamics or probe those dynamics more than another task, but it has nothing to do with my cognitive ontology of continuous and discrete and retrieval and working memory, whatever, right? And everything to do with just some sort of description, abstract description at the level of cortical cerebellar interactions. And if that's true, then yeah, this is sort of a fool's path, trying to come up with tasks that work or don't. So yeah, yeah. Anyway, that's a really long non-answer, because I think that question, your question might sound specific because it's about adaptation, but I think it actually is just another version of the general question.
Yeah, it is indeed. Thanks.
Sam, Harsha had a question for you as well.
Yeah.
I'll read it for
it's
you. It's on the chat. I can read it for you. Can you speculate a bit more on what is the cerebellar contribution that affects the pace of mental rotation specifically with respect to the analogy to dysmetria? You didn't see accuracy deficits.
Yeah, good point. So we actually did see some accuracy deficits, but not in every experiment consistently. So that's a good point. Maybe what's happening is, because there is some sort of, abstractly using the word, but maybe because there's some sort of dysmetria in the mental rotation, the subject sort of does a kind of accounting that like they'll take more time to do the mental rotation, but they'll still make sure they get it right. So in other words, it is a speed accuracy trade-off, but it's not a speed accuracy trade-off that happens at the level of different rotation sizes, like the control analysis I showed, but a more sort of general kind of task strategy that like, this is really hard for me to mentally rotate, but I'm going to go through my dysmetric mental rotation, get to the end and get the answer right. So in that sense, I think, you could spin the dysmetric thing in a way that it doesn't produce accuracy deficits necessarily, because it is ultimately a really easy task, right? Once you mentally rotate the letter, however laborious it is for you to mentally rotate the letter, once you do, you're just saying whether it's like a normal alphabetical letter or a mirror rotated one. And actually, I think I don't know, because of our task is just button presses, but I suspect that most of the errors we see are actually, could actually be like action slips. So they just, they press the wrong button or forget the mapping. I don't know. I mean, it was the two arrow keys on the keyboard. So they weren't actions that are that far apart from each other. We wanted to avoid having it be like a bimanual task, but I think in retrospect, we could have made the response. So it's a good question. I don't know, but I think like a sort of speed accuracy trade-off.
That's nice. Well, all right. I so much enjoyed it, Sam. You did such an excellent job. You taught me so much. I'm so glad you had this chance. Thank you, everybody, for joining us. Next week is SFN, so we won't have a meeting. I hope you have a great Tuesday.
Thanks, Reza. That was really fun. And thanks, everyone, for watching. It was really a fun time.